Hi, so welcome to the conducting system of the heart and some information about ECGs or EKGs. We are going to be focusing on exercise 31 from the lab manual and giving a little bit of background about that as we get ready for our heart dissection. When we talk about the conducting system, it is an intrinsic conducting system, meaning that the heart is in control of its own beating. And it has pacemaker cells that are going to do that. It's going to, we're going to see one single heartbeat here. And that heartbeat is going to allow for the heart to contract in series. So the atria will contract first, the ventricles will contract second, and blood will be expelled from the heart. The goal here is that one contraction cycle or one heartbeat occurs, fully ends, and then another heartbeat can begin. This is the pacemaker. We have these autorhythmic cells of our pacemaker, and those autorhythmic cells are going to, see if I can highlight that again, our autorhythmic cells are going to allow for this automaticity, which means that the heart can beat on its own without input from our nervous system. Now there is input, there is going to be obviously our sympathetic parasympathetic innervation where we are speeding or slowing the heart. But this autorhythmicity is that our pacemaker cells can make their own beat for the heart. The other cells that are really important here are contractile cells. Now our contractile cells are going to produce the contractions that actually expel the blood. Okay, so we are going to see our contraction pushing from the atria to the ventricles and then pushing from the ventricles out to our pulmonary and our systemic circuits. So we have different parts of our conducting system, and if you go to page 450 in exercise 31 of your lab manual, we can walk through these parts together. Okay, so your sinoatrial node or your SA node is found in the right atrium. The sinoatrial, we can zoom in. The sinoatrial node found in your right atrium, okay, this is the pacemaker of the cell. This is what we consider the pacemaker of the cell. This is where your heartbeat contraction is going to begin. Now, these are your internodal pathways. The internodal pathways will spread the impulse from the SA node on to the AV node or this atrioventricular node. The atrioventricular node sits right on the border of the atria and the ventricle. So the right atria and the right ventricle. The AV node will grasp the impulse coming from the SA node along these internodal pathways and send the impulse down the AV bundle to these bundle branches. Now this is running along your interventricular septum between the right ventricle and the left ventricle. Once we get down towards the apex of the heart, we're going to see these Purkinje fibers. Now the right ventricle, if you remember, has the moderator band. The moderator band here will be innervated, and the papillary muscles of the left ventricle and right ventricle. The Purkinje fibers are going to spread that impulse or conduct the impulse up towards the base of the heart. If you think about, right, this is your little crown of your base of the heart, this is your apex, we are conducting upwards in order to expel blood out of these ventricles. Once the impulse reaches these Purkinje fibers at the apex of the heart and begins to spread along those fibers, these will cause the contractile cells to contract in the heart, and that is following through with this contraction coming from your pacemaker or your SA node. Now it's important to note here that our regular action potential that we're used to seeing from our skeletal muscles isn't in play here. Our impulse is going to look a little bit different. That's due to this pacemaker potential. Our pacemaker potential is going to be the fact that there is just this gradual depolarization towards the threshold going on. Okay, so because our pacemaker cells are going to be in control of the heartbeat, and the contractile cells will be following through with that impulse action reactivity. The fact that this threshold can be met with the help of this pacemaker potential, we're not staying at rest here, right? We're going to see this depolarization, and that is where we'll see our heartbeat. And when we come back to rest, the pacemaker potential will allow this gradual depolarization towards the threshold. That allows the pacemaker cells to be a little bit more in control. We're not starting from rest. We're just gradually reaching that threshold until another heartbeat occurs. This pacemaker potential that we're talking about is going to be this slight drift towards that threshold, right, that we just saw in the graph. Now, that gradual depolarization that's occurring is going to be because of this slow inflow of sodium. And you have a slow inflow of sodium without this compensating outflow of potassium. If you remember, we talked about last semester the fact that the equilibrium potential of sodium is much higher, it is in the positive, right? Positive 60, and the equilibrium potential of potassium is much lower, negative 90. So if we sit at our resting membrane potential of about negative 60 for our cardiac contractile cells, and we have a slow influx of sodium coming in, then we're going to be moving slowly towards the threshold where we can see a depolarization. Now, typically we're going to see this depolarization occurring where action potentials are occurring about 60 to 100 beats per minute, 61 to 100 times per minute. Okay? The AV node will not depolarize as quickly. It will be slower, and it will only be about 40 to 60 action potentials per minute. Now, the SA node is quicker to reach the threshold. That's why it can reach more action potentials per minute. And that SA node establishes our sinus rhythm, or our heart rhythm. This is the rhythm that we're going to be looking at when we look at our EKGs and we start to read the EKGs through. So we're going to follow along here with the conduction through the heart starting at the SA node. And we're going to see the ECG or EKG tracings that will go along with it. Okay? Our ECG, or our electrocardiogram, is going to trace the electrical activity of the heart and trace the contractions of the atria and the ventricles. And the goal here is to have a normal EKG reading or ECG reading. Now, the great thing about ECGs is that we can see what is normal on them, but we can also see what is abnormal on them. So the fact that we can look at an ECG tracing and find abnormalities in the heart that could help us explain and diagnose the patient is extra important. So we're going to begin here with the SA node activity in the conducting system. The SA node, remember, is your pacemaker, and it is producing about 60 to 100 action potentials per minute when we are at rest. If you look at the ECG tracing, it is going to be this portion where we are at rest before a heartbeat is going to begin. We're going to scroll down here. Okay, once that pacemaker, those pacemaker cells have generated this action potential, this impulse, they're going to travel the internodal pathways. Now we are going from the right to the left side, and the goal here is to head towards the AV node. It takes about 50 milliseconds for the impulse to travel the internodal pathways and reach this AV node that it is at this border of the ventricles and the atria. This is going to be, this stimulus, this electrical impulse is going to be measured as our P wave on our ECG. This is your atrial depolarization. Moving down, there is going to be a 100 millisecond delay at the AV node. Now, this is going to be caused because the atria have to fully relax before the ventricles can contract. So we see about 100 millisecond delay, and then we're going to see this slight shift towards this PR interval. This is what we call our PR interval, where we are conducting from the internodal pathways to the AV node. We'll have a 100 millisecond delay, and then we're going to have the AV node conducting to the AV bundle. That 100 millisecond delay is going to be, again, so the atria can relax before the ventricles contract, but it's also going to allow for the flooding of the calcium into that sarcoplasmic reticulum so that we can begin our contraction of our ventricular contractile cells. Then we're going to move along to this Q wave. This dip here after the PR interval is the Q wave. The Q wave is the beginning of our ventricular depolarization. So we're going to have our impulse that has traveled to that AV bundle, traveling down the interventricular septum to the bundle, along those bundle branches. And we're heading towards the apex, and we're heading towards the Purkinje fibers at the apex. The moderator band here, which helps to pull those papillary muscles of that right ventricle, is going to be affected at this point. Okay, and that moderator band, remember, is pulling on the papillary muscles to pull on the chordae tendineae so that we can keep the tricuspid valve closed during ventricular ejection. Now, when we look at this QRS complex as a total here, okay, the Q is the beginning of that ventricular depolarization. The R is the full ventricular depolarization, and we have our little S dip here as well. Okay, so QRS complex is what you're looking at when you're looking for your ventricular depolarization. The impulse will have traveled along the bundle branches to the apex of the heart, and the Purkinje fibers will then be passing along to those contractile cells of the myocardium, the muscle cells of the ventricles. Our atrial contraction will be fully completed, and your ventricular contraction will begin. This is going to be the longest portion of your ECG reading or your contractile period. Now, once your full ventricular depolarization occurs, we do have this ST interval to measure and this T wave. The T wave here is when the ventricles repolarize. Okay, so they are going to repolarize, they're going to head back to rest, and then we are going to have our resting point in between our heartbeats. Okay. Again, we're starting at this P wave. We're going to measure this PR interval. That's the first thing we're going to look for. Then we're going to look for our QRS complex. Does it look normal? Do we have a full Q and S wave? And can we measure this ST interval and see a full T wave where our ventricles will repolarize? So we can use the ECG readings to help with our diagnosis when we're looking at a patient's reading. We're going to be looking for, first, if this P wave exists and is it normal. Second, is our PR interval normal? Third, is our QRS complex normal? And then how long between this T wave ending and this P wave beginning, what is that distance? We're going to measure those. Now, when you look at this R wave, if this R wave is abnormal, if it's too high, you might be looking at something like enlarged ventricles. But if you end up with this ST interval being raised up, so too much higher than our P wave area that is raised up here, then we could be looking at something like an MI or myocardial infarction. If you measure your PR interval and your PR interval is too long, then we could be seeing a blockage in the heart where we're not having connectivity between the SA nodes and the AV nodes as strong as we should have, for example. Okay, so we're going to look and measure all of these waves and distances. If we're too fast, over 100 beats per minute, we're looking at tachycardia. If we are below 60 beats per minute and we're too slow and this S wave distance here is too long, then we could be looking at bradycardia. And fibrillation is going to be just irregular asynchronous beating, where we're having no connectivity between our SA node and our conducting contractile cells. where you lose that synchronicity, so you end up with just a wavy pattern on our ECG. Come back and join me for part 2.